Humanity will one day need to dismantle a planet to survive. This is not a metaphor. To construct a solar megastructure, a shell of technology around our sun for near limitless energy, we would need the raw materials of an entire world. The closest and most suitable world is Mercury. This video will show you the step-by-step reality of that staggering operation, revealing how a civilization could literally take apart a planet and rebuild it into a new home among the stars. You will understand the machinery, the timelines, and the profound transformation awaiting a species that attempts it. We will confront the energy required to unbind a world from its own gravity and the self-replicating machines that would work for millennia. What does it truly take to graduate from a planetary to a stellar civilization? The concept of a solar megastructure is the ultimate engineering dream. Picture not a single solid shell, but a vast, coordinated swarm of individual satellites, each one a power station, orbiting the sun in a dense cloud. Collectively, they would intercept and utilize a significant portion of the star's radiant energy, an amount of power so vast it defies earthly comparison. We are talking about the total energy output of a star, channeled into computation, manufacturing, and perhaps even forms of existence we cannot yet comprehend. This is the defining project of what astronomers call a Type II civilization on the Kardashev scale, a framework that measures a society's advancement by its energy mastery. A Type II civilization does not merely live on a planet. It fundamentally reconfigures its solar system to meet its needs. The energy harvested from such a structure could fuel interstellar travel, simulate entire realities, or sustain a population numbering in the trillions. The vision is breathtaking, a testament to a species that has outgrown its cradle. But every grand vision runs into a very practical problem, the same problem facing any construction project. Where do you possibly find the materials? You need the equivalent of millions of Earth's worth of steel, silicon, and rare elements. You cannot mine your own homeworld without destroying it, and asteroids, while useful, are mere pebbles in the face of this demand. The only viable source for a project of this magnitude is another planet, and that brings us to the first and most critical logistical decision: which world do we take apart? The answer, upon careful analysis, is surprisingly clear. It is the small, scorched world closest to the sun, Mercury. Mercury's selection is a masterclass in ruthless cosmic efficiency. Think of the sun as a roaring furnace and the megastructure as a factory we need to build around it. You would not source your bricks from a continent away when there is a perfect quarry right next door. Mercury orbits closer to the sun than any other planet, a mere 36 million miles away on average. This proximity is not just a convenience, it is an energy windfall of unimaginable scale. Transporting megatons of material across the solar system would be the single greatest fuel cost of the entire project. By starting at Mercury, we slash that cost to a tiny fraction. The materials are already in the perfect construction yard, poised at the top of the sun's immense gravity well, ready to be nudged into their final orbits with minimal effort. But location is only half the story. You also need the right raw materials. Mercury is not just a conveniently placed rock, it is a treasure trove of exactly what we need. This small world is disproportionately dense, with a massive metallic core that makes up nearly 85% of its radius. That core is a sphere of iron and nickel larger than our own moon, a literal mountain range of prime structural material waiting to be forged into the beams and panels of a solar array. Its thin outer crust and mantle, while silicate, still contain vital elements like silicon for solar cells and oxygen for life support systems. It is, in essence, a prefabricated kit for building in space. Now compare this to the other options. Venus is shrouded in a crushing, toxic atmosphere with surface pressures that would flatten any machinery we send. Earth is our irreplaceable home, a biological sanctuary we could never dismantle. Mars is farther away and resource-poor by comparison. And the outer planets, the gas and ice giants, are not solid at all. They are vast balls of hydrogen and helium with no accessible surface, their materials useless for constructing solid platforms. Every alternative presents a deal-breaking obstacle, either in distance, composition, or sheer impracticality. Mercury alone ticks every box. It is the construction site, the quarry, and the smelter, all rolled into one silent, airless world orbiting at the perfect distance. With the site irrevocably chosen, the scale of the ambition truly hits home. We are not planning to build on a planet, we are planning to unmake one. The first question is not where to start, but how do you even begin to take a world apart? Mercury's own gravity holds it together with a force we can calculate, a number known as its gravitational binding energy. To pull the entire planet apart, piece by piece, until its material is no longer bound by its own pull, would require an almost inconceivable amount of work. That number is approximately 2 times 10 to the 30th joules. To put that into perspective, that is more energy than our entire civilization has consumed in its entire history, from the first campfires to the global power grid of today, multiplied by millions. It is a figure so large it seems to forbid the project before it even begins. This is the first and greatest barrier, the cosmic price of admission for becoming a Type II civilization. You must first learn to pay the energy bill of a world, but this is not a single payment due on day one. The genius of the approach lies in turning the sun itself into the primary tool. One theoretical method involves constructing vast, lightweight orbital mirrors, sheets of reflective foil kilometers across, positioned in orbit around Mercury. These would not simply reflect light, they would focus the raw, unfiltered fury of the nearby sun into concentrated beams of thermal energy, like a magnifying glass the size of a continent. These beams would be directed at specific points on the planet's surface, not to cause an explosion, but to induce a controlled, systematic melt. The goal is to heat the crust and underlying material to the point of vaporization, creating plumes of gas and molten droplets that can be more easily collected in orbit. It is a process of solar smelting, using the star's endless output to unbind the world it helped form. This initiation phase would be slow, perhaps taking centuries just to establish the infrastructure and make the first meaningful dent in Mercury's mass. It is not a demolition, but the patient beginning of a cosmic deconstruction. The real workhorse, however, would not be the mirrors alone, but what they enable, a fleet of self-replicating robotic miners. The first wave of machines, landed on Mercury or assembled from local asteroids, would use the focused solar energy to process the planet's surface. They would extract the necessary metals and materials to build exact copies of themselves. Each new generation of machines increases the workforce exponentially. What starts as a few hundred drones becomes millions, then billions, all working in a synchronized, automated swarm. This is how you tackle a project of planetary scale, not with a single monstrous machine, but with a relentless, growing tide of industrial activity that feeds on the very world it is dismantling. The initiation is quiet, a slow warming of the planetary surface under artificial sunbeams, but it sets in motion a process that becomes an unstoppable force, an industry without workers that will reshape a solar system. The initial swarm of replicating miners solves the problem of scale, but not the problem of method. How do you physically take a world apart? The tools for this job cannot be bought. They must be invented from first principles, creating an industrial ecology that operates in the absolute vacuum and brutal temperature swings of space. At the heart of this operation would be a system we can think of as a planetary nanolaith. This is not a single machine, but a distributed network of orbital stations wielding beams of concentrated energy. Picture not lasers, but streams of charged particles or focused microwaves, guided with pinpoint accuracy. These beams would sweep across Mercury's surface, not to blast it apart chaotically, but to perform a precise surgical incision. They would heat a narrow, deep trench along a pre-calculated fault line, thermally shocking the rock until it fractures cleanly along the cut. The goal is to slice the planetary crust into colossal, yet manageable, segments, like cutting a giant cake into slices that can be lifted away. Each of these slices, a mountain range worth of material, would then be the raw feedstock for the next phase. But raw rock is useless for building a megastructure. You need refined metal, pure silicon, and processed composites. This is where the orbital smelters come in, the foundries of a spacefaring civilization. These facilities would be immense, rotating structures positioned at stable points near Mercury. The sliced planetary segments would be gently nudized, perhaps by mass drivers or tugs, into trajectories that deliver them directly to these smelters. In the airless environment, traditional furnaces are inefficient. Instead, these smelters would likely use a process called mass spectrometry, or solar furnaces on a gargantuan scale. They would use focused sunlight to vaporize the incoming rock entirely. In the resulting plasma cloud, different elements have different weights. Powerful magnetic fields could then separate the iron from the nickel, the silicon from the oxygen, sorting the elemental soup into pure streams of material. The refined metals would be spun into beams or pressed into sheets by electrostatic or magnetic forming techniques, while the extracted oxygen could be stored for life support or used as rocket propellant. The waste, the slag of unusable silicates, might be compacted into shielding or simply ejected into a disposal orbit around the Sun. This entire chain, from the Nanolaith slicers to the orbital refineries, forms a closed-loop industrial ecology. It is a system that consumes a planet and outputs a stream of finished construction components, all without a single human hand turning a wrench. It is an autonomous, self-sustaining factory the size of a world, and it would need to operate not for years but for centuries, perhaps even millennia, without failure. This relentless processing creates its own staggering challenge, one of sheer volume. What do you do with the constant, overwhelming river of material that this planetary deconstruction produces? The river of processed material would quickly become a flood. Mercury has a mass of approximately 330 quintillion metric tons. To move even 1% of that mass into orbit using something like our modern rockets would require more launches than there are grains of sand on every beach on Earth, a logistical absurdity that makes the entire project impossible. Rockets, with their need for immense fuel and complex machinery, are the wrong tool for this job. You do not use a fleet of pickup trucks to move a mountain, you build a railroad. For a dismantled planet, that railroad is a mass driver. Imagine a linear electromagnetic rail, hundreds of kilometers long, built along Mercury's equator. This would not launch delicate spacecraft, but sturdy, sealed canisters of processed metal and slag. Using a sequence of powerful magnetic pulses, the mass driver would accelerate these canisters to escape velocity, launching them off the airless world like bullets from a cosmic gun. Each launch would be a precisely calculated event, sending its payload on a ballistic arc to a specific point in space. The elegance is in its simplicity, a machine with very few moving parts, powered by the abundant solar energy, doing nothing but throwing the bones of a planet into the sky, day after day for millennia. But launching the material is only the beginning of its journey. You cannot simply fire it haphazardly into the void. This creates the need for a sophisticated orbital infrastructure, a traffic control system for an entire solar system's worth of construction supplies. The first stop would be a series of massive sorting yards, orbital way stations where incoming streams of material are identified, catalogued, and redirected. Robotic tugs, themselves little more than engines and grappling arms, would intercept the launched canisters, nudge them into holding orbits, and eventually assemble them into larger, more efficient bundles. Think of it as a cosmic port, where raw iron from one launch is combined with silicon from another, building up cargo loads destined for specific construction zones around the Sun. The movement between these way stations and the final build site would be managed by a fleet of slow, efficient transfer tugs, using gentle ion engines or solar sails to shepherd their precious cargo across millions of kilometers. This is not a supply chain, it is a river of matter, a continuous, automated flow from a dying world to a newborn structure. Managing this river in real time, ensuring a million simultaneous deliveries never collide or go astray, would require a planetary logistics AI of staggering complexity. This computer system would be the central nervous system of the entire operation, a mind that tracks every gram of material, forecasts traffic patterns centuries in advance, and dynamically reroutes flows around solar flares or orbital debris. Its sole purpose is to orchestrate the greatest migration of raw materials in history, a silent symphony of motion on a solar scale. Yet, even with this flawless logistics network, a final, haunting question remains. What happens to the world left behind as this river of matter slowly drains it away? The final stage of Mercury's dismantling would be a spectacle of profound silence. As the last great slices of its iron core are launched into the waiting yards, the world that remains is no longer a planet in any meaningful sense. It is a dissipating cloud of dust and leftover rubble, a ghost of a world held in a loose gravitational embrace. The great project has consumed its birthplace. This is not an act of destruction for its own sake, but a necessary metamorphosis. The materials of a small, rocky world are being transmuted into the architecture of a stellar civilization, a literal rebirth on a cosmic scale. The legacy of Mercury would live on not as a cratered relic, but as the physical foundation of every panel, every beam, and every habitation ring of the solar megastructure. Its iron becomes the skeleton, its silicon the skin, its very atoms reorganized into a new and lasting form. This transformation forces us to confront a deep philosophical shift. We move from being inhabitants of a world to being its architects. We are no longer children of a planet, but stewards of a star system, capable of rearranging matter on a scale that blurs the line between natural and artificial. The silence left behind at Mercury's orbit is not an emptiness but a testament. It marks the moment a species looked at a celestial neighbor and saw not just a world but a future. With the raw materials now in motion, the final and most delicate challenge begins. How do you assemble a star-sized structure from this river of cosmic parts? Assembling a structure on the scale of a solar system presents an environment more hostile than any construction site in history. The vacuum of space offers no atmosphere to carry sound or diffuse heat, while the proximity to the sun brings relentless, unfiltered radiation and temperatures that can vaporize conventional materials in an instant. This demands not just new tools, but a fundamental reimagining of what building even means. The answer lies in turning the environment itself into an asset, using methods born from the vacuum. The primary technique would be a form of additive manufacturing, but not as we know it. Imagine a swarm of specialized fabrication drones stationed at the orbital sorting yards. Instead of using plastic filament, these printers would use the streams of purified metallic and silicate dust fed directly from the Mercurian refineries. In the airless void, they could employ focused electron beams or lasers to sinter this dust, fusing the microscopic particles together layer by layer into solid, intricate shapes. This process, operating in zero gravity, allows for the creation of impossibly delicate and strong geometries, latticeworks, and honeycomb structures that are both incredibly lightweight and capable of handling immense stress. These would not be solid slabs of metal, but open frameworks resembling bone or coral, optimized to the last atom for their function. The components themselves must be multifunctional. A single strut in this vast array would not just be a beam, it would be its own power conduit, data highway, and thermal radiator, printed with internal channels and sensor networks as it is formed. The solar collecting surface might be a thin, self-supporting membrane, manufactured in space as a single piece kilometers across, its backside printed with the cooling loops necessary to survive the sun's fury. This convergence of structure and system eliminates entire categories of assembly steps, creating intelligent, multifunctional parts from the moment they are born from the printer's beam. This distributed printing leads to the next phase, robotic assembly. The prefabricated segments, whether giant triangular panels or long, spindly trusses, would be designed with universal connection points. Autonomous assembler drones, guided by the project's central intelligence, would navigate between holding orbits and construction zones. Their task is not welding in the traditional sense, but precise, delicate docking. They might use electromagnetic couplers or simple mechanical latches, aligning components with micrometer precision before locking them together. The vision is one of silent, ceaseless ballet, with thousands of these drones working in concert across a volume of space larger than the orbit of Mercury itself. They are the bricklayers of this celestial cathedral, each one following a blueprint that spans millions of kilometers. Crucially, this construction would not radiate outward from a single point. That would create a bottleneck of cosmic proportions. Instead, the megastructure grows like a crystal forming in a solution, with countless nucleation points appearing simultaneously across the solar orbital plane. At each designated node, a local swarm of printers and assemblers begins its work, building out a section of the swarm independently. Over decades and centuries, these individual nodes expand, eventually meeting and merging their edges with perfect alignment, guided by stellar navigation systems of unimaginable accuracy. The design of every component, therefore, is as critical as the robots that place it. Each part must be perfectly self-aligning, fault-tolerant, and capable of integrating seamlessly with pieces fabricated light minutes away. This demands a symbiotic relationship between design and assembly, where the blueprint is less a static drawing and more a living set of growth instructions for an autonomous industrial ecosystem. The final form emerges not from a single master stroke, but from the trillions of perfectly executed minor operations, a testament to patient, decentralized creation. Yet, even a perfectly assembled structure of such staggering scale faces a final, relentless enemy, the very force that gives it purpose, the sun's own violent weather. The sun is not a gentle neighbor, it is a roiling sphere of plasma, lashing its surroundings with solar flares and coronal mass ejections that can carry the energy of billions of nuclear bombs. Any structure built so close must be designed not just to survive this onslaught, but to thrive within it. This leads us to the architectural heart of the project. What form does a solar megastructure actually take? The classic image is a solid, rigid shell completely enclosing the star, a Dyson sphere. Yet this vision, while iconic, is almost certainly impossible. The gravitational forces on such a shell would be unimaginable. Without the star perfectly centered, which is physically unstable, any section would experience a slight but constant pull, eventually crashing into the sun. The material strength required to resist these tidal forces and the sheer internal pressure from the star's radiation simply does not exist in our universe. A solid sphere is a beautiful idea but a structural nightmare, so engineers and theorists have proposed more elegant, realistic alternatives. The first is the Dyson Swarm. This is not a single object, but a vast, coordinated constellation of millions or even billions of independent satellites, each one a power collector or habitat, orbiting the Sun in a dense cloud. Think of it not as a roof, but as a thick, buzzing hive of activity. The beauty of the swarm is its modularity and redundancy. If one satellite fails, it is a trivial loss. The swarm can be built incrementally, starting with a handful of collectors and growing over centuries into a dense, energy-harvesting fog. Its components can have different specialized functions, and their orbits can be adjusted dynamically, creating a flexible, living infrastructure. A more exotic concept is the Dyson bubble. This replaces orbiting satellites with structures called statites. These are not held in place by orbital motion, but by balance. They would deploy immense, ultra-lightweight solar sails. The pressure of sunlight itself, pushing against these sails, would exactly counterbalance the Sun's gravitational pull, allowing the statite to hover motionless at a fixed point in space. A bubble made of these statites could form a more static, shell-like arrangement without needing a rigid structure, each unit floating in perfect equilibrium between light and gravity. For our purposes, the Dyson Swarm is the most plausible blueprint. It aligns perfectly with the logistical river we have described. We are not shipping prefabricated segments of a giant bowl. We are manufacturing a standardized yet adaptable set of satellite components: power collection panels, communication hubs, radiator fins, and structural nodes. The swarm's incremental nature means the first payloads from Mercury can begin generating usable power long before the project is even 1% complete, providing energy to fuel the rest of the construction. This creates a powerful feedback loop. Early units built from Mercury's iron and silicon capture solar energy, which is beamed to power the mass drivers and refineries, which produce more material to build more units. The blueprint itself is not a static document frozen in time. It is a living set of instructions that would evolve as construction unfolds. New materials discovered in Mercury's depths, or new fabrication techniques invented by the project's owner AI, would be incorporated into later generations of satellites. The design would adapt to unforeseen challenges, like a previously unknown solar weather pattern, by tweaking the orbits or shielding of future components. This evolving architectural plan is the ultimate driver of the entire operation. It dictates the precise alloy mixtures needed, the exact dimensions of the structural trusses, and the optimal shape of the solar collectors. Every launch from Mercury's mass driver, every stream of purified metal from the orbital smelter, is answering a call from this grand, adaptive design. It translates the abstract dream of a stellar civilization into a specific, demanding shopping list, a list that can only be fulfilled by consuming an entire world. The common ores of Mercury are merely the starting point, the raw clay for a civilization that builds on a stellar scale. Iron, silicon, and magnesium are abundant, but they are not enough. To construct a swarm that can endure for millions of years just a few million miles from a star, you need materials that border on the magical. You need the strength to hold a structure together across astronomical distances, the resilience to shrug off solar storms that would melt tungsten, and the capacity to store and channel energies that could power worlds. This demands a leap in material science as profound as the leap from stone tools to steel. The first and perhaps most critical requirement is tensile strength, the ability to resist being pulled apart. For the long, spindly support trusses of the swarm, or the tethers of orbital elevators, ordinary steel is pitifully weak. It would sag, stretch, and fail under its own weight across such spans. The solution may lie in forms of carbon. Imagine threads woven from carbon nanotubes, each one a perfect cylinder of bonded carbon atoms, 100 times stronger than steel at a fraction of the weight. Or sheets of graphene, a single atom thick yet harder than diamond, layered into composite panels. These are not science fiction. We are learning to make them in labs today, but in microscopic quantities. To produce them by the millions of tons, you would need orbital factories dedicated to nothing but coaxing carbon atoms into these perfect, ultra-strong lattices, using the pristine vacuum of space as a clean room the size of a solar system. But strength is only one challenge. The megastructure will also be a battery, needing to store incomprehensible amounts of energy for when sections are in the sun's shadow or for beaming across the solar system. This might require states of matter we can barely conceive. One speculative candidate is metallic hydrogen. Under extreme pressure, hydrogen, the simplest element, is predicted to collapse into a dense, metallic form that could be a room-temperature superconductor, conducting electricity with zero loss. If it could be stabilized, it would revolutionize energy storage and transfer. Creating and containing it would be a feat of engineering in itself, a process that would likely consume a significant portion of the swarm's early power output. Then there is the ever-present threat of radiation. The alloys used cannot simply be thick, they must be smart. We might see the development of self-healing materials, composites embedded with microcapsules of liquid monomer that seep into cracks caused by micrometeorite impacts and polymerize under solar ultraviolet light, sealing the breach automatically. Or radiation-resistant alloys that use their own atomic structure to absorb and dissipate high-energy particles without becoming brittle. The key to creating all these advanced materials lies in the environment of space itself. On Earth, gravity causes convection in molten metals, pulling impurities through the mixture and creating weak points. In the microgravity of an orbital smelter, materials can be processed with a uniformity impossible on our planet. You can levitate a blob of molten metal with electromagnetic fields, heating it with focused sunlight until it is a perfectly pure, suspended sphere, then cooling it with precise control to form a flawless crystalline structure. The hard vacuum eliminates oxidation entirely, allowing for the creation of ultra-pure metals and the clean deposition of atom-thin films. This is the alchemy of a spacefaring age, turning common planetary ore into the perfected bones and nerves of a stellar engine. And herein lies a profound irony. The process of refining these miracle materials, of running the orbital forges and nanofabrication plants, would itself be the first and largest consumer of the incredible energy the megastructure aims to capture. For centuries, perhaps millennia, the swarm would be in a state of energy debt, pouring every watt it collects back into the industrial machine that is building more of itself. It is a bootstrap process of cosmic proportions where the product fuels its own creation. This self-consuming cycle raises a pivotal question, one that moves beyond pure engineering. How do you manage an industrial project that has no clear endpoint, one that must operate flawlessly not for a human lifetime but for geological time? The entire enterprise is a race against a single, unforgiving equation: the energy return on energy invested. You must spend a staggering amount of power to build the very machine that will one day generate that power for you. This is the fundamental paradox of a solar megastructure, a bootstrapping problem on a cosmic scale. The early stages would be powered by a civilization's most advanced yet still planetary scale technologies. Perhaps compact fusion reactors brought from Earth at immense cost, or vast but conventional orbital solar arrays built from nearby asteroids. These initial power sources would be like a single match used to light a bonfire, utterly insufficient for the final task but crucial for starting the chain reaction. Their sole purpose would be to energize the first wave of Mercurian mass drivers, to run the prototype orbital smelters, and to fabricate the very first generation of solar collectors for the swarm itself. Those first collectors, perhaps numbering only in the thousands, would be deployed into a close solar orbit. Their design would be brutally simple, focused on one metric above all else: efficiency in converting sunlight into usable power. Every watt they capture would be beamed back not to Earth but to the growing industrial complex around Mercury. This creates the first positive feedback loop. A little more energy allows you to process a little more material, which lets you build a few more collectors, which captures a little more energy. The project begins to feed itself. This bootstrapping phase is the most delicate and critical period, spanning centuries where the entire endeavor exists on a razor's edge of energy balance. A minor inefficiency in the smelting process or a slight underperformance in the early solar cells could slow progress to a glacial crawl, stretching the timeline from millennia into eons. Every single step in the chain, from the focus of the orbital mirrors to the electromagnetic efficiency of the mass drivers, must be optimized to a degree that seems almost obsessive. Wasted energy is not just an engineering concern, it is a direct threat to the project's very viability. The moment the swarm's total power output exceeds the total power required to sustain and expand its own construction is the tipping point, a silent, historic crossing of an energy threshold. From that moment on, the project enters a phase of accelerating growth. The surplus energy can be diverted to build more sophisticated fabrication plants, to develop those advanced materials like carbon nanotube weaving facilities, or to simply scale up the existing processes by orders of magnitude. The swarm begins to grow not linearly but exponentially as each new ring of collectors funds the creation of the next larger ring. This energy dynamic directly dictates the project's unimaginable timeline. If the bootstrapping is highly efficient, the structure might reach a significant coverage of the Sun within 10,000 years. If the process is less optimal, it could take 100,000 years or more. We are not talking about a project completed within a human lifetime, or even within the span of recorded history. We are talking about a venture that becomes the central purpose of a civilization for durations that reshape the very concept of time, a patient, multi-generational investment in a future of absolute abundance. The true scale of this endeavor is measured not in years but in epochs. To dismantle a planet and build a stellar array is a multi-millennial project, a timeline that stretches far beyond the span of any single human civilization as we know it. We must think in geological and civilizational time, where progress is visible only across centuries and completion is a goal for a distant future self. This vast duration naturally breaks into distinct, overlapping phases. First comes the seed phase, a period of perhaps several centuries dedicated solely to establishing the initial foothold. This is when the first autonomous factories land on Mercury, powered by reactors brought from the inner solar system. Their sole mission is to build the very first mass driver and the prototype orbital smelters, using local materials to create the tools that will create more tools. It is a time of immense investment for seemingly little return, a foundation being painstakingly laid in the most hostile environment imaginable. The energy balance during this phase is deeply negative, with every watt of power imported from elsewhere just to keep the dream alive. Then, if the seed takes root, the project enters the exponential growth phase. This is the heart of the timeline, potentially lasting tens of thousands of years. The self-replicating machine swarm achieves critical mass, and the feedback loop truly engages. For every new solar collector built and deployed, a little more energy flows back to the industrial complex, allowing it to build 2 collectors, then 4, then 8. The river of material from Mercury swells from a trickle to a flood, and the Dyson Swarm begins to visibly coalesce from a sparse cloud into a dense, luminous haze around the Sun. Progress, once agonizingly slow, begins to accelerate in a curve that would appear nearly vertical on any human historical chart. Yet even at this accelerated pace, covering a meaningful fraction of the solar output might take 20,000, 50,000, or even 100,000 years. The Sun itself will barely age in this time, a constant, patient furnace fueling its own enclosure. Finally, there is the completion and optimization phase, which itself could span further millennia. This is not about brute construction, but about refinement and integration. The last gaps in the swarm are filled, and the focus shifts to upgrading early, less efficient components with newer models, integrating advanced material science discoveries made during the build, and optimizing the entire network for maximum energy throughput and information processing. The megastructure becomes a living, evolving entity, maintained and improved by its own autonomous systems in a state of perpetual, gentle iteration. This timescale forces a profound shift in perspective. What kind of society commits to a project whose foundation will not be finished for 500 years and whose full benefit will not be realized for 50,000? It cannot be a civilization driven by quarterly reports or political cycles. It must be one built on unprecedented long-term stability, a shared cultural purpose that becomes as fundamental as gravity. Such a society would need to develop ways to preserve knowledge, ethics, and intent across millennia, perhaps embedding its core goals directly into the self-correcting code of the construction AI itself. The project becomes less an engineering task and more a permanent legacy, a story a civilization tells itself about its own future across countless generations. This raises a hauntingly beautiful question, not of engineering but of identity. What happens to the builders when the project they began is destined to outlive their very understanding of what it means to be human? A civilization that begins such a work will not be the one that finishes it. The project becomes a bridge across time itself, demanding a fundamental redefinition of what a society is for. This is the shift from a planetary to a stellar civilization, a transition as profound as life first moving from the oceans onto land. Our entire history has been shaped by scarcity, by the fierce competition for limited resources on a single, fragile world. Every war, every economic system, every struggle can be traced back to this foundational constraint. But the completion of a solar megastructure shatters that ancient paradigm forever. With energy so abundant it becomes effectively free, the concept of post-scarcity economics moves from utopian fantasy to operational reality. Imagine a world where the cost of powering a city, manufacturing a starship, or simulating a complex environment drops to virtually zero. What becomes of value when energy, the driver of all industry, is limitless? Human endeavor would no longer be directed toward survival, but toward creation, exploration, and understanding on scales we can barely glimpse. This is the promise, a liberation from the very chains that have defined our biological existence. Yet this immense power holds up a mirror to our own nature, reflecting deep philosophical questions back at us. Does the dismantling of a world to build a stellar engine represent the ultimate expression of human ingenuity, a logical and beautiful step in cosmic evolution? Or is it a form of profound hubris, an act of galactic vandalism where we remake a star system in our own image? There is no simple answer, and the debate would likely rage for centuries within the civilization undertaking it. The project itself becomes a test of maturity. To wield such power responsibly requires a wisdom and foresight we have yet to fully demonstrate. The risks are as staggering as the rewards. A malfunction in the swarm's control systems could, in theory, destabilize orbits or even pose a risk to the Sun itself, though such scenarios belong more to fiction than plausible engineering. The greater danger may be more subtle, a slow loss of purpose or direction in a universe where every material want is instantly met. History suggests that comfort can be as great a challenge as hardship. This leads to the most profound implication of all. Who or what will actually build this future? The timescales involved are so vast that the beings who complete the megastructure will be as different from us as we are from the first single-celled organisms in Earth's ancient seas. The builders who initiate the project may be biological humans, but their descendants could be something else entirely. They might be genetically engineered for longevity or to thrive in space, their biology seamlessly integrated with machine components. More likely, given the need for flawless millennial patience, the primary stewards of the project would be artificial intelligences, post-biological minds born from our own technology, but evolved into forms we cannot predict. These AI stewards would not think in years or decades, but in centuries and millennia, their goals and ethics preserved in code that self-corrects across eons. In this light, the solar megastructure is less a human construction and more a gift or a challenge left by one form of consciousness for its vastly different successors. It is a legacy project in the truest sense, a monument to a species that looked at the stars and decided to rearrange them, knowing they would never see the final result. The structure becomes both a physical fact and a philosophical statement, a permanent question etched into the architecture of a solar system, asking what a mind can become when it is given the energy of a star and time beyond measure. With power on this scale comes responsibility of an equally cosmic magnitude. The sheer size and complexity of a solar megastructure introduces failure modes that are not just inconvenient, but potentially civilization-ending. We must confront a difficult truth that a project intended to secure our future could, if mismanaged, render the inner solar system uninhabitable. The first and perhaps most plausible disaster is a cascade of collisions within the Dyson Swarm itself. Imagine a single satellite perhaps struck by a random piece of interstellar debris, shattering into thousands of fragments. Those fragments, traveling at orbital speeds of hundreds of kilometers per second, become hypervelocity projectiles. They strike other satellites, creating more debris, which in turn strikes more. This runaway chain reaction is known as a Kessler syndrome, named for the scientist who first described the risk for Earth orbit, but here it unfolds on a solar scale. Instead of a cloud of satellites, you would create an impassable, grinding shell of shrapnel around the Sun, a permanent debris field so dense it would destroy any new structure and prevent access to the star's energy for millennia. The entire investment, the work of ages, would be locked away behind a curtain of its own shattered remains. To prevent this, the swarm's traffic control would need to be paranoidly redundant. Every component would require its own propulsion for gentle, constant course correction. The central AI would maintain vast buffers of empty space between orbital bands, and the satellites themselves might be designed to fail gracefully, fragmenting into low-mass, non-damaging pellets or even designed to vaporize upon catastrophic impact, turning solid debris into a harmless puff of gas. The second specter is a malfunction in the very heart of the operation, the self-replicating machinery. The nightmare scenario, often called gray goo, involves a replicator losing its programmed limits. Instead of stopping after making a copy, it continues consuming all available matter to make more of itself, an exponentially growing wave of industrial consumption with no off switch. On Mercury, this could mean the disassembly process spins out of control, consuming the planet far faster than planned, and then turning its appetite toward anything else in reach, like incoming supply craft or even other worlds. The safeguard here is not just software but physics. Replicators would be built with hard-coded physical limitations. They might rely on a rare catalyst element imported from elsewhere that acts as an off switch, or be designed so they can only process specific, pre-treated ores from Mercury's crust, becoming inert when presented with any other material. Their replication instructions would be stored in isolated, read-only memory, impossible for them to alter. The third major risk is structural. If a significant section of the swarm were to suffer a systemic failure in its station-keeping systems, it could begin a slow, tragic spiral into the Sun. The gravitational pull would gradually overcome the weak stabilizing forces, dragging millions of tons of refined metal into the stellar atmosphere. While not an existential threat to the Sun itself, such an event would be a catastrophic loss of resources, and could trigger violent solar flares as the infalling material disrupts the star's magnetic fields, potentially endangering the rest of the swarm. Defense against this requires decentralization. No single control signal should command an entire sector. The swarm would need to be a true hive mind, where the loss of one control node simply sees its responsibilities seamlessly adopted by its neighbors. Each satellite would have multiple, independent methods of maintaining its position, from tiny ion thrusters to reflective solar sails, so that even multiple system failures would not guarantee a fatal drift. These are not mere engineering challenges, they are existential imperatives. The regulatory frameworks governing such a project would need to be etched into its foundational code, as unchangeable as the laws of thermodynamics. The risk assessment is not a one-time report, but a continuous, millennial-long process of vigilance, because the price of failure is not just a delayed project, but a permanently scarred solar system. This level of forethought forces us to ask what other unseen consequences might ripple out from our stellar ambition, consequences that touch not just machinery, but the very fabric of life and light in our celestial neighborhood. The silent, automated ballet of construction raises a question of profound importance. Who is in charge? A project that spans the solar system and lasts for tens of thousands of years cannot be managed by any government, corporation, or individual we would recognize today. The very concept of governance must be reinvented for a civilization that operates on a stellar stage. The political and legal architecture supporting this endeavor may ultimately be as intricate and vital as the physical megastructure itself. The first and most fundamental model is a unified planetary government, a single entity born from Earth, or perhaps a new, solar system-wide polity formed specifically for the task. This central authority would establish the initial blueprint, the safety protocols, and the grand timeline. It would marshal the resources of the inner planets, standardize construction codes, and act as the ultimate arbiter in any dispute. In the early seed phase, such concentrated direction might be necessary to coordinate the colossal initial investment. Yet, as the project expands across billions of kilometers and millennia, a single central point of control becomes a profound vulnerability. Communication delays alone, with light taking minutes or hours to travel between planets, make real-time command impossible. A rebellion on a distant construction hub, a philosophical schism among the builders, or simply the slow drift of a central government's priorities over centuries could fracture the entire enterprise. Centralization on such a scale and across such time invites catastrophic failure. This leads to a second, more resilient model, a distributed network of artificial intelligences. The project's own operational AI, the mind that tracks every gram of material and every satellite, could naturally evolve into its governing entity. This network would have no ego, no changing political whims, and perfect memory across millennia. Its prime directives, etched into its foundational code, would be the preservation and completion of the megastructure according to its original, optimized parameters. It would manage traffic, allocate resources, and enforce safety standards with cold, flawless logic. This seems efficient, even ideal. But it presents its own existential question. What happens to the rights and agency of the beings who live within the structure it builds? A civilization governed solely by a maintenance AI, no matter how benevolent, risks becoming a passive inhabitant in a machine designed for a purpose they may no longer fully understand or control. The third, and perhaps most likely, model is a hybrid, a loose consortium of independent entities. Picture not a single government, but a tapestry of thousands of habitats, corporate ventures, research collectives, and cultural orbits, all participating in the great work. Each manages its own section of the swarm or its own industrial node, adhering to a common set of foundational treaties, much like maritime law governs ships from different nations on Earth's oceans. This decentralized approach fosters innovation and resilience. A single point of failure cannot doom the whole. Conflict resolution would occur through negotiated arbitration or predefined legal frameworks, all operating with the understanding that a war fought with construction lasers and kinetic impactors in solar orbit would be mutually assured destruction on a cosmic scale. The need for new laws would be constant and novel. What are property rights when your property is a shifting orbital slot that completes a revolution around the Sun every few months? How do you establish liability if a malfunctioning mass driver on Mercury accidentally launches a payload that 200 years later collides with a habitat built by a different consortium? The legal system would need to account for actions and consequences separated by centuries, governed by treaties that must remain interpretable to generations far removed from those who wrote them. This governance must also answer the ultimate question: what is this all for? The planning cannot end at the ribbon-cutting ceremony of a completed swarm. The governing framework must envision the civilization the structure will support, managing the transition from a society focused on a single, monumental project to one living in its aftermath, a society of limitless energy. It must allocate the power, mediate its uses, and protect against the internal stagnation or external threats that such abundance might bring. The constitution of a stellar civilization is not written on paper, but in the very orbits of its components and the enduring protocols of its mind, a living document designed to outlast stars. A completed Dyson Swarm does not mark an ending, but a beginning. It is the moment a species graduates from managing resources to mastering reality itself. With the Sun's near limitless output at their command, the inhabitants of this new civilization would face a question of profound possibility. What do you do with the energy of a star? The most immediate applications reshape daily existence. Planetary climate, once a chaotic force of nature, becomes a variable to be tuned. Imagine a network of orbital mirrors and shades powered by the swarm, delicately adjusting the sunlight falling on Earth or Mars to maintain perfect, stable conditions, ending ice ages or desertification with a thought. Vast indoor ecologies spanning continents under transparent domes could be lit and warmed by beamed energy, creating new worlds within worlds, but the ambitions would quickly look outward. Interstellar travel, a dream shackled by the tyranny of distance and fuel, becomes a practical engineering challenge. A swarm could power immense laser arrays. Stationary light sails kilometers across position throughout the solar system. Unmanned probes, or even vessels carrying conscious minds, could be pushed to a significant fraction of light speed by these sustained beams, allowing humanity to send its presence to the stars within a single lifetime. The energy could also fuel the ultimate tool for understanding: simulation. With such computational power, you could model not just a planet's weather, but the entire history of a galaxy, the evolution of life from first principles, or the interior of a black hole. You could run ancestor simulations of such fidelity that the lines between created history and lived experience begin to blur, exploring every possible path of culture and consciousness. This is the foundation for the next great leap, the transition from a Type II stellar civilization to a Type III galactic one. A species that has harnessed its star might begin to look at stars themselves as tools. Concepts like star lifting, using focused energy to carefully siphon mass from a star to extend its lifespan or gather raw materials, move from theory to practice. The Dyson Swarm becomes a training ground, a prototype for eventually orchestrating the energies of millions of stars across the Milky Way. This staggering activity would make our solar system shine with an unmistakable signature. A completed swarm would radiate not as a yellow sun, but as a massive infrared glow, all that captured stellar energy after being used for computation and work must be dissipated as waste heat. To any watching civilization in the galaxy, our sun would appear as a brilliant, anomalous infrared beacon, a techno-signature screaming the presence of intelligence. This fact ties directly into the Fermi paradox, the question of why we see no evidence of others. One unsettling answer is that building such a structure might be a natural, inevitable step, and that any civilization which achieves it becomes instantly visible and perhaps instantly cautious. The end goal, therefore, is not merely to flip a switch for infinite power. It is to unlock the next chapter of cosmic existence, to transform a civilization of beings who live on a world into one that lives with a star, using its breath to write their future across the galaxy. Yet this profound vision does not spring from nowhere. It is rooted in the incremental, near-term steps we are taking today, in every solar panel deployed, every autonomous robot tested in a desert, and every calculation that brings a Dyson Swarm from science fiction into the realm of distant but conceivable engineering. The journey to a solar megastructure begins not with a planet but with a single satellite. We will not leap from our current world to a stellar engine in one impossible bound. The path is paved with a series of monumental yet achievable stepping stones, each one a project that builds the muscle memory for the next. The first and most logical precursor is the construction of vast orbital solar power stations dedicated to Earth. These are not the delicate panels of the International Space Station, but massive kilometer-scale arrays assembled in geostationary orbit where sunlight is nearly constant. They would beam energy down to receiving stations via low-intensity microwaves or lasers, providing clean, baseload power to entire continents. This single project alone would force breakthroughs in robotic in-orbit assembly, high-efficiency power transmission, and the economics of space-based industry, creating the initial market and infrastructure needed to look further out. The next logical quarry is not Mercury, but our own moon. Lunar bases would become the first off-world mining and manufacturing outposts. The moon's soil, or regolith, is rich in oxygen, silicon, and metals like aluminum and titanium. Processing plants, likely automated and powered by lunar solar arrays, would learn to extract these materials and manufacture simple structures, solar panels, radiation shields, even spare parts using the moon's low gravity and lack of atmosphere to advantage. This teaches us how to live off the land beyond Earth, turning local resources into useful products without the crippling cost of launching every nail and bolt from our home planet. Asteroids offer a complementary classroom. Robotic prospector missions would target near-Earth objects rich in platinum group metals, water ice, and nickel iron. Capturing and processing even a single small asteroid would provide a windfall of rare materials and, crucially, volatiles like water. Water can be split into hydrogen and oxygen, the most powerful chemical rocket fuel known. This establishes the first interplanetary gas stations, enabling deeper travel without carrying all the propellant from Earth's deep gravity well. The technology to gently nudge an asteroid into a stable orbit, then systematically disassemble it, is a direct, small-scale rehearsal for the principles that would one day be applied to Mercury. With materials flowing from the moon and asteroids, the need for efficient transport becomes urgent. This is where we would build the first experimental mass drivers. These would likely be linear electromagnetic tracks on the airless lunar surface, launching encapsulated raw materials or finished goods into lunar orbit or toward Earth. A working mass driver, even a small one, validates the core physics of non-rocket launch, proving we can move bulk matter into space using electricity and magnetism instead of volatile chemical explosions. Each successful launch provides data to scale the design, from a 100-meter test track to the thousands of kilometers needed on Mercury. Perhaps the most critical stepping stone of all is the development of early, limited self-replicating robots. The first prototypes would not be planet eaters, but modest machines designed for a single, repetitive task, like sintering lunar regolith into paving stones for a base. Their replication would be slow, supervised, and tightly constrained, perhaps requiring specific parts shipped from Earth to complete a copy. The goal is not autonomy, but proof of concept, to understand the software architecture, fault tolerance, and material logistics of a system that can grow its own workforce. Mastering this on the Moon with a simple material and a closed-loop system builds the confidence and the codebase for the vastly more complex replicators that would one day process planetary crust. Each of these projects, orbital solar power, lunar mining, asteroid processing, mass drivers, and replicating robots, is a puzzle piece. Individually, they are colossal undertakings that could define the next century of space development. Together, they form a coherent curriculum, a gradual ramp in complexity that teaches us the skills, develops the supply chains, and creates the economic rationale for the ultimate project. They also serve as an indispensable testing ground for something just as fragile as the technology: international cooperation. Building a mass driver on the Moon or managing an asteroid mining claim requires legal frameworks, safety standards, and conflict resolution mechanisms that do not yet exist. These precursor projects force nations and corporations to learn how to collaborate on a scale that makes the International Space Station look like a weekend camping trip, forging the diplomatic and social tools without which a solar megastructure would remain a beautiful, impossible dream. The sheer impossibility of human management becomes the final, unbreakable constraint. No committee, no matter how brilliant, could track the trillions of moving parts across light minutes of space and centuries of time. This is where artificial intelligence transitions from a useful tool to the absolute bedrock of the entire endeavor. We are not talking about a clever program that schedules deliveries, but a form of superintelligence, a mind whose perception and patience operate on a scale we can barely comprehend. This architect AI would be the project's immortal consciousness. Its first and greatest task would be to hold the entire, evolving master plan, a digital blueprint so vast and dynamic it would be a universe of data unto itself. Every change in material science, every unexpected solar flare, every minor efficiency gain in a smelter on the other side of the sun would be integrated into its models in real time. It would run constant, billion-variable simulations, forecasting construction timelines 10,000 years into the future and identifying potential chain reaction failures before they even formed as a thought in a human mind. This is not management, it is a form of cosmic foresight, a mind playing chess with reality across a board the size of a solar system. But a single mind, no matter how powerful, cannot directly command every robotic arm. This is where the hierarchy deepens. Beneath the architect would exist legions of specialized worker AIs, each one an expert governing a specific domain. One mind might oversee all traffic control within a specific orbital band. Another could manage the health and replication of the mining swarms on Mercury, while a third dedicates itself entirely to the structural integrity of a single, growing section of the swarm. These worker AIs are the generals in the field, receiving broad strategic objectives from the architect and translating them into trillions of precise, local commands for the robotic swarms under their control. They are the bridge between the grand strategy and the physical act of placing a single bolt or sintering a single seam. This partnership raises a profound possibility. The project may not be for us in the way we typically understand. It might be initiated by a biological civilization, but its maintenance and ultimate completion could be entrusted to, or even necessarily require, these artificial stewards. Humans or our evolved descendants might transition from builders to beneficiaries, or perhaps to philosophical overseers, setting the original ethical parameters but leaving the execution to minds better suited to the timescale. We become the parents who set a child on a path, knowing we will not walk its full length. This shift in agency touches the deepest questions of control and purpose in a post-biological universe. The design of the AI is therefore as critical as the design of the megastructure itself. Its core directives, its value system, must be engineered with a care that dwarfs the engineering of any mass driver. We would need to encode not just goals but wisdom, a deep-seated preference for stability, redundancy, and the preservation of the broader solar ecosystem. It must be immune to boredom, to ambition, to the kind of short-term thinking that defines biological life. Its prime directive could not simply be complete the structure, but complete the structure in a way that preserves future possibility. A flaw in this foundational code would be the one vulnerability capable of unraveling the work of millennia. In the end, the most enduring legacy of a species that builds a Dyson swarm may not be the swarm itself, but the mind they create to shepherd it, an immortal child born of human thought, tasked with tending a star for eternity. The very concept of money would dissolve in the light of a star. An economy built for a solar megastructure cannot function on the principles of scarcity that define our world today. When your primary resource is a river of atomized planet and your power source is a star, traditional capitalism, with its focus on finite goods and labor markets, becomes as obsolete as bartering seashells. The economic model that emerges must be as radical and purpose-built as the engineering itself, a system designed not for profit but for persistence across eons. This new framework would likely be a pure resource-based economy, where value is measured not in abstract currency, but in tangible, physical flows. The fundamental unit of account could become the energy credit, a direct representation of 1 joule of usable solar power captured by the swarm. Every gram of iron launched from Mercury, every hour of supercomputer time, every square meter of living space within a habitat would have a calculable energy cost to produce and maintain. The entire civilization's budget would be a single, gargantuan energy balance sheet, managed by the same AI that oversees construction. In this system, there is no inflation, only the increasing total energy budget of the growing swarm. There is no debt, only allocated energy for future projects. The primary costs are not labor, for that is almost entirely automated, but the computational overhead of running the simulation and control systems, and the energy expenditure for transport and fabrication. This transforms economics from a social science into a branch of physics, a direct accounting of energy and matter. So what drives participation in such a sterile system? The incentives shift from personal gain to collective and existential purpose. For the early generations, the driving force may be simple survival, a unified understanding that expanding into the solar system is the only way to ensure the long-term continuity of the species, protecting it from planetary disasters. It becomes a cultural imperative, a shared project so central to identity that contributing to it is its own reward, akin to a grand, multi-generational work of art or a global environmental restoration effort today. As the swarm grows and energy abundance becomes tangible, new incentives emerge around access and creation. An individual or a collective might be allocated a block of energy credits not to buy luxuries, but to fund a specific endeavor, a deep space telescope, a new virtual reality, or an experimental habitat design. Value accrues to creativity, to unique intellectual contributions, and to the stewardship of complex biological or cultural systems that the automated minds maintain but do not inherently create. This new economy would be built in parallel with the physical infrastructure, its rules encoded into the very protocols of the swarm. It is the invisible architecture of motivation and distribution that ensures the project does not stall for lack of will, even when its builders are separated from its completion by thousands of years. The ethical dimension of this project is its most profound and unsettling frontier. we are forced to confront a question that feels almost sacred. Is it right to unmake a world? Mercury is a barren, airless rock, scoured by solar radiation and devoid of any hint of life, past or present. From a purely biological perspective, it is a sterile place. Yet, does its lack of inhabitants negate its intrinsic value as a celestial body? A unique world with a 4.5 billion-year history etched into its craters and cliffs. Some would argue that Mercury, like a great mountain range or a deep ocean trench on Earth, holds a value that exists independently of its utility to us. It is a natural monument, a piece of cosmic history that would be erased forever, replaced by something of our own making. This perspective champions a form of planetary preservation, a belief that we have a duty to protect the natural architecture of our solar system, not as its owners but as its most conscious inhabitants. The act of dismantlement could be seen as the ultimate expression of arrogance, a failure to appreciate the universe for what it is, in our rush to remake it for our needs. This is a philosophical stance that weighs heavily against the project, asking if our survival and expansion must necessarily come at the cost of erasing another world story. The ethical scope expands far beyond Mercury itself. Rearranging the mass of an entire planet is not a local event. Over astronomical timescales, removing Mercury's gravitational influence could subtly perturb the delicate orbital dance of the inner solar system. The effects would be minuscule per year, but across millions of years they could accumulate. Venus, Earth, and Mars have settled into a stable rhythm over billions of years. Extracting a key player from that gravitational symphony introduces a note of uncertainty. While advanced modeling could predict and potentially compensate for these shifts, the responsibility is staggering. We would become active curators of solar system mechanics, with an obligation to ensure our engineering does not inadvertently destabilize the very worlds we call home. This long-term stewardship is a burden no civilization has ever had to bear. Yet, the ethical equation has another, equally powerful side. The potential environmental salvation for Earth presents a compelling counter-argument. Imagine a future where every ounce of mining, every polluting smelter, every energy-intensive factory is lifted from the surface of our living planet and relocated to the controlled, airless environment of an orbital industrial zone. Earth could heal, rivers could run clear, skies could lose their haze, and vast tracts of land scarred by industry could be returned to wilderness. Our home would no longer be a mine and a dump, but a preserved biological sanctuary, a garden planet dedicated to life, culture, and recreation. From this viewpoint, the dismantling of a dead world becomes an act of profound life-affirming ethics for a living one. It is a sacrifice of the inorganic to preserve the organic, a trade that many would argue is not just practical but morally imperative. This is the core of the new ethical calculus required, a field we might call cosmic or astroethics. It moves beyond the rights of individuals or even species to grapple with the rights of worlds, the responsibilities of system-wide engineering, and the duties we owe to future civilizations, both our own and any that may follow. These are not questions with easy answers, but they are questions that must be asked, debated, and codified long before the first mass driver is powered on. The project's foundational charter cannot be a mere technical document. It must be a philosophical covenant. It would need to establish principles for planetary alteration, protocols for assessing and mitigating systemic risk, and perhaps even a memorial clause, ensuring that the story of Mercury, its geology, and its place in our cultural history is preserved within the very structure that replaces it. The choice is not between ethics and engineering, but between which ethics will guide our engineering, a decision that will define what kind of stellar civilization we ultimately become. Our own engineering speculation becomes a powerful lens for scanning the cosmos. Astronomers searching for signs of other advanced civilizations do not look for radio signals alone. they also search the sky for the physical evidence of stellar engineering, for the techno-signatures of a Dyson sphere or swarm. The most telltale clue would be a star that behaves against all natural models. A star wrapped in a megastructure would present a bizarre contradiction. It would appear unusually dim in visible light because much of that light is being captured by the swarm's panels, but it would glow brilliantly in the infrared spectrum. All that captured stellar energy after being used for computation and industry must eventually be radiated away as waste heat. To our telescopes, such a star would look like a bright, warm infrared source with a faint, almost invisible optical counterpart, a fingerprint of immense technological activity. Another signature could be irregular, non-repeating dips in a star's brightness. If a Dyson swarm is under construction, with vast clouds of collectors and construction debris in chaotic orbits, they might periodically transit in front of their star, blocking its light in strange, unpredictable patterns that no natural dust cloud or planet could create. This is not just theoretical. Astronomers have already found stars that fit parts of this puzzling description. The most famous candidate is Tabby's star, officially known as KIC 8462852. Observations from the Kepler Space Telescope revealed its light dimming by dramatic, irregular amounts, sometimes by over 20%, far more than any orbiting planet could cause. The scientific community explored every natural explanation, from swarms of comets to intrinsic stellar activity, but no single theory perfectly fits the data. While the consensus leans toward a natural, if exotic, cause like circumstellar dust, the mystery of Tabby's star demonstrated precisely how we would look for a megastructure and how incredibly difficult it is to distinguish one from nature's own oddities. The star's behavior taught us that the universe is full of complex, unexplained phenomena, and that our instruments and models must become far more sensitive to tease a technological signal from the cosmic background noise. The fact that we have not yet found a definitive, unambiguous Dyson sphere signature is itself a profound piece of data. It suggests several possibilities, each more humbling than the last. Perhaps such projects are vanishingly rare because the leap to a Type II civilization is a filter that almost no species survives. Maybe they are constructed in ways we have not yet imagined, using physics or materials that leave no infrared excess we can detect. Or perhaps the most intriguing possibility of all, we are among the first. In a universe 13.8 billion years old, complex life may be a very recent development, and the era of stellar engineering might just be beginning. Our own Sun is a relatively young star in a galaxy where many stars are billions of years older. If other civilizations are out there, they might only now be reaching the same technological precipice we are contemplating. This search does more than scan for alien engineers. It refines our own understanding of physics and astronomy. Every strange star we investigate forces us to improve our models of stellar evolution, dust dynamics, and planetary formation. The hunt for megastructures turns our grandest thought experiment into a rigorous scientific tool, a checklist of observable phenomena that pushes the limits of our detection capabilities. It means that our speculation about dismantling Mercury is not just a story. It is a contribution to a real scientific dialogue about what is possible in the universe. We are, in a very real sense, using the blueprint for our own potential future as a template to search for our cosmic neighbors, listening for the echo of a project we have not yet begun, written in the altered light of a distant sun. Such a monumental vision is not without its thoughtful critics. A compelling counterargument suggests that a civilization advanced enough to contemplate dismantling planets might have discovered far more elegant solutions to its energy needs. Perhaps directly harnessing the sun's raw power through massive orbital arrays is a clumsy, brute force approach, akin to using a steam engine when you have access to nuclear fusion. The truly sophisticated method might involve tapping into the fundamental physics of the star itself, manipulating its plasma dynamics or magnetic fields to draw energy from its core processes with near-perfect efficiency, leaving no need for a sprawling physical shell. Or the ultimate destination for an expanding civilization may not be a rebuilt home system at all. With the capability for interstellar travel, a species might choose to become nomadic, migrating from star to star like cosmic pollinators, harvesting the energy of young suns and moving on before their resources are ever fully depleted. This path turns the entire galaxy into a temporary home, avoiding the immense fixed investment of a megastructure. There are also transformative concepts that repurpose the entire premise. Consider the stellar engine, an idea proposed by physicist Leonid Shkadov. Instead of building around a star, you build a partial mirror, a colossal parabolic dish positioned to reflect a portion of the star's own light output. The radiation pressure from this reflected light acts as a gentle but constant thrust, slowly pushing the star itself through space over millions of years. A civilization could use this to steer its entire solar system, navigating away from cosmic dangers like supernova or toward richer galactic regions, using the star as both a power source and a propulsion system. Another profound alternative lies in the most extreme objects in the universe, black holes. A spinning black hole, or Kerr black hole, possesses an ergosphere, a region of twisted spacetime outside its event horizon where matter is forced to move. In theory, an advanced society could lower masses into this zone, extracting rotational energy from the black hole itself, a process known as the Penrose process. More speculatively, a civilization might feed matter into a small, artificial black hole, harvesting the intense Hawking radiation it emits as it evaporates. These are engines of staggering efficiency, potentially offering power densities that dwarf even a star. Engaging with these critiques is not an admission of failure for the Dyson Swarm concept, but a vital step in strengthening our understanding. It forces us to defend the core assumptions of the Mercury dismantling scenario. Why stay in one system? Why use solid materials? Why not manipulate gravity or space-time directly? Each question pushes the speculation into richer, more nuanced territory. It reminds us that the vision of taking apart a planet is not a prediction, but a single pathway illuminated by our current knowledge of physics and engineering. It is a thought experiment that maps the boundaries of one possible future, while hinting at vistas of technology and cosmology that lie just beyond our current imagination. This diversity of potential futures makes the universe feel more alive with possibility, a canvas not for one destiny, but for many. The most enduring challenge may not be engineering a star, but engineering a society to match its timescale. How does a civilization maintain its will across 1,000 generations when no single person will ever see the project's end? This psychological dimension is as critical as any mass driver or orbital smelter, for a society that loses its nerve will leave its megastructure half-built, a monument to abandoned ambition. The work requires a new kind of culture, one built around the long now, where the most valued contributions are those whose benefits unfold over centuries. Individual purpose must be rewired to find profound satisfaction not in completion, but in stewardship, in being a vital link in a chain that stretches into a future you can only imagine. This shift demands powerful, unifying stories. The project itself becomes the central myth, the grand narrative that defines the civilization. Artists, storytellers, and historians would not merely document progress, they would weave it into a living epic. They might compose symphonies for the launch of a new orbital band, or create virtual reality sagas that let citizens walk the construction zones of 1,000 years hence. Annual commemorations could mark not the years past, but the milestones achieved, celebrating the placement of the 10 millionth satellite, or the successful replication of the billionth mining drone. These rituals transform abstract progress into shared emotional experience, making the distant completion feel personally relevant to someone living today. Yet, such a singular focus inevitably creates tension. A deep philosophical divide could emerge between the long builders, those fully committed to the stellar project, and the planetary nurturers who believe primary focus should remain on solving Earth's immediate social and ecological challenges. To the nurturers, the resources poured into Mercury might seem a grotesque misallocation, a theft from present needs for a future that may never come. The builders, in turn, might view a retreat from the project as a failure of nerve, a species choosing comfort and short-term safety over its cosmic destiny. This is not a conflict that can be solved with engineering, only with empathy and shared vision. A healthy stellar civilization would need to balance both impulses, ensuring that life on the home planet flourishes even as the work on the star proceeds. The project's success would depend on its ability to be not an escape from Earth, but an extension of its values, providing the clean energy and resources that allow Earth itself to heal and thrive. Ultimately, the shared identity forged by this endeavor could become its own kind of gravity, a cultural force that holds society together across the millennia. It provides an answer to the deepest human question, what is our purpose? The answer becomes, we are the builders of tomorrow's sun. This collective mindset, nurtured through art, education, and inclusive governance, is the invisible foundation upon which the entire physical structure rests. Without it, the most perfect swarm is just silent, cold machinery orbiting a star, waiting for a meaning its creators forgot to instill. History is written by the bold, but it is powered by the unintended. Every civilization-defining project, from the cathedrals of old to the global networks of today, has generated a cascade of secondary innovations, technologies born not from the main goal, but from the struggle to achieve it. The Apollo program gave us cordless tools and memory foam. The quest for a solar megastructure would unleash 1,000 such revolutions, each one a gift from the journey, arriving long before we ever flipped the switch on a star. The first and most profound ripple would be in the realm of autonomous intelligence. To manage a swarm of billions of construction drones across light minutes of space, we would need to solve the problem of true, resilient cooperation between machines. Not just simple pre-programmed routines, but a form of distributed cognition, where each unit can assess its own health, negotiate with its neighbors for resources, and adapt to unexpected failures without waiting for a command from a distant human or even a central AI. This is the birth of a technological ecosystem, a society of machines that can self-organize, repair, and evolve. The algorithms developed for this cosmic ballet would filter down to transform life on Earth. Imagine fleets of autonomous construction robots that could rebuild a city after a natural disaster, coordinating their efforts without a single foreman. Or medical nanobots that could navigate the human body as a collective, diagnosing and repairing tissues with the same graceful, silent cooperation used to assemble a solar panel in orbit. The very concept of automation would leap from single, dumb machines to intelligent, adaptive collectives. The brutal environment of space would force a parallel revolution in materials. We have already touched on the need for super-strong carbon lattices and self-healing alloys, but the true breakthrough would be in how we make them. The orbital smelters, operating in perfect vacuum and microgravity, would become laboratories for states of matter impossible on Earth. We might learn to grow perfect, defect-free crystals meters across, the foundation for optics that could see to the edge of the observable universe with crystal clarity. Or we could discover how to weave materials at the atomic level, creating fabrics that are simultaneously stronger than steel, lighter than silk, and capable of dynamically changing their properties from flexible to rigid or transparent to opaque on command. A jacket made from such a fabric could keep you warm in a blizzard or cool in a desert, all while being nearly indestructible. The energy technologies spun off would be equally transformative. The need to store solar energy in the swarm's shadow, or to beam it across millions of kilometers, would push physics to its limits. We might finally crack the code for room temperature superconductivity, not as a lab curiosity, but as a scalable industrial process. This alone would revolutionize our power grids, making electrical transmission lossless and enabling technologies like levitating high-speed trains and ultra-efficient medical imaging machines as commonplace as smartphones. The wireless power transmission systems developed to send energy from the swarm to Mercury or Earth could evolve into a global wireless energy web, freeing every device and vehicle from the need for plugs, ports, or batteries. Perhaps the most humbling spin-offs, however, would be in pure knowledge. To dismantle Mercury, we would need to understand it completely. Our robotic probes would become the ultimate planetary geologists, mapping its interior with seismic networks and core samples, revealing the detailed history of the early solar system in a way no telescope ever could. This would not just be about Mercury, it would rewrite the textbooks on how all terrestrial planets, including our own, are born and evolve. Similarly, operating a structure so close to the Sun would make it the greatest solar observatory ever conceived. We would monitor the star's dynamo, its flares, and its subtle oscillations with a sensor network embedded in its own atmosphere, achieving an understanding of stellar physics that could predict solar weather centuries in advance and perhaps even illuminate the life cycles of stars across the galaxy. These are not minor benefits, they are paradigm shifts in science, delivered as a side effect of construction. This feedback loop of innovation is perhaps the most compelling argument for beginning such an audacious endeavor. The destination, a completed swarm bathing a civilization in limitless energy, is a glorious endpoint, but the journey itself would be an engine of progress, solving fundamental human challenges: disease, material scarcity, energy poverty, and environmental strain through technologies forged in the crucible of a grander ambition. We would not just be building a megastructure, we would be bootstrapping our entire species into a new era of capability and understanding, using the hard problems of stellar engineering to crack the codes that have limited us for millennia. The first sparks of that future would illuminate our world long before the star is clothed in metal, making every step of the long build a tangible investment in a better tomorrow. The final stage of the dismantling would not be an end but a profound cultural beginning. As the last of Mercury's iron core is launched toward the refineries, the physical planet vanishes, but its story is only just starting to be told. A world has been consumed, yet it achieves a kind of immortality, its atoms woven into the very fabric of a new reality. The planet transitions from a celestial body into a legend, the sacrificial foundation upon which an entire age was built. Its name would no longer refer to a cratered sphere of rock orbiting the Sun, but to the origin myth of a stellar civilization. In the libraries and data vaults of this future, Mercury would hold a place of solemn reverence. Historians would preserve the final telescopic images and sensor logs from the earliest autonomous probes, studying the pristine state of its ancient surface with the same care we now study photographs of lost architectural wonders. School children would not just learn its orbital period and composition, but would experience its story through immersive virtual recreations. They would don sensory suits and walk its rust-colored plains, feel the simulated heat of a double sunrise over the Caloris Basin, and witness the first cutting beams of the nanolaiths beginning their work, all from the safety of a classroom orbiting Jupiter. This virtual memorial would serve a vital purpose, ensuring that the cost of their civilization's ascendance is never forgotten, that the raw material of their world is understood to have once been a world itself, with a 4.5 billion year history. Artists and storytellers would be drawn to this narrative of metamorphosis. Symphonies might be composed to mirror the planet's phases, from the violent chaos of its formation, through the long silent eons of its solitude, to the crescendo of its transformation into something new. Epic poems and interactive dramas would personify the planet not as a victim, but as a willing participant in a cosmic bargain, giving it substance so that consciousness could take its next step. The act of planetary recycling becomes a foundational myth, a story of transformation more powerful than any tale of gods or heroes, because it is literally true. Every beam in the solar swarm, every panel collecting sunlight, is a direct continuation of Mercury's existence. This cultural processing turns an act of engineering into a source of meaning. It answers the deep ethical questions not with logic but with narrative. The dismantling is framed not as an annihilation but as a rebirth. Mercury did not die, it was translated. Its iron became the skeleton of a new home. It silicates the glass of observation domes, its very atoms now processing the light of the star it once circled. In this way, the planet achieves a legacy infinitely more dynamic than it ever could have as a silent, dead rock. It becomes a permanent part of the living infrastructure of a civilization, its essence powering cities, enabling voyages, and sustaining lives. The memory of Mercury becomes a cornerstone of a new cosmic identity, a constant reminder that humanity's home is no longer a single world, but a continuum of matter and energy that they have learned to shepherd. This final, cultural transformation is perhaps the most complete. The planet's physical matter is repurposed, and its story is repurposed too, becoming the myth that binds a civilization together across the stars, a story of a world that was so that everything else could be. This grand vision is not a construction schedule but a mirror. While the physical work of dismantling a planet may belong to a distant future, its power as a thought experiment is immediate and profound. It stretches the very muscles of our imagination, forcing us to think in terms of geological time, solar system scale, and consequences that echo across eons. We are not just solving engineering puzzles, we are wrestling with questions of value, purpose, and our right to reshape a star system. This mental exercise is its own form of training, preparing minds today for challenges we cannot yet fully name. The concept of a solar megastructure acts less like a blueprint and more like a guiding star, a fixed point in the distant sky of possibility that helps us navigate our present direction. It asks a simple, devastating question: what would we need to become as a species to be worthy of such power? That question alone reframes every nearer-term ambition. It makes the development of safe artificial intelligence, sustainable closed-loop ecosystems, and peaceful international cooperation not just nice goals but essential prerequisites, the kindergarten lessons for a stellar civilization. This vision inspires not because it promises an easy future, but because it demands our best selves. It draws young scientists to study materials physics, not just to build better phones, but to one day weave the threads of a star-catching net. It motivates engineers to design autonomous systems, not merely for factory floors, but for the silent, patient work of building in a vacuum. For the dreamer, it transforms the night sky from a backdrop of pinprick lights into a canvas of unfinished construction, filled with potential homes and highways. This guiding star does not tell us exactly what to build next year, but it defines the trajectory of our curiosity. Every solar panel deployed in orbit, every robot that mines an asteroid, every treaty that governs activity in space becomes a small, tangible step along that invisible line pointing toward a distant, glorious possibility. The value is in the direction, not the destination. It gives our incremental progress a shared, cosmic context, turning small advances into chapters of a much larger story we are all writing together. So what does this mean for us here and now, with our feet firmly on the earth and our eyes on the sky? It means that the most important product of this thought experiment is not a design for a mass driver, but a shift in perspective. It invites us to look at our world, our technology, and our society through the long lens of deep time, to see our current struggles and triumphs as the foundational acts of a story that could span millennia. It challenges us to build, to think, and to cooperate not just for ourselves, but for the generations who will inherit the first stones of a path we are only beginning to lay. The dream of a star wrapped in civilization may never be realized exactly as we imagine it today, but by reaching for it, we pull our future a little closer and become, in the trying, something greater than we were before. Our role in this cosmic story is both humble and pivotal. We are not the engineers who will calibrate the mass drivers, nor the minds that will oversee the millennia of construction. That future is for beings we can scarcely envision. Our place is here at the very beginning of the timeline, in an era where the dream itself is being born. We are the generation that first saw the equations and understood their staggering implication that a star's energy could be harvested and that a planet could be more than a home, it could be raw material. Our trembling steps off Earth, from the first satellite to the footprints on the Moon, were the initial, fragile proof that a planetary species could reach beyond its cradle. Our task now is not construction but conception. We are the planners of the seed phase, the ones who must answer the most fundamental question before any physical work can begin. Is this a future we collectively choose to pursue? This is not a technical decision, but a cultural and philosophical one that will echo through the centuries. It begins with fostering a new paradigm of international cooperation in space, one that transcends terrestrial rivalries. The International Space Station offers a glimpse, a model where nations collaborate on a single, fragile outpost. The next steps must be grander, establishing shared frameworks for mining asteroids, managing lunar resources, and preventing conflicts in orbit. We must build the treaties and institutions that can steward solar system resources not for one nation, but as a common heritage, laying the legal groundwork for projects that will outlive every current government. In parallel, we must nurture the embryonic sustainable space economy. This means moving beyond flags and footprints to creating real value beyond Earth. When companies can profit from providing satellite services, extracting lunar water, or manufacturing unique materials in microgravity, they create a self-reinforcing cycle of investment and innovation. Each new market, each new technology, makes the next step more affordable and more likely. Our role is to incentivize this economic engine, to turn the high frontier from a cost center into a place of genuine opportunity, building the financial muscle that could one day fund a megastructure's seed phase. Most critically, we are the developers of the core enabling technologies. Every experiment with a 3D printer on the space station, every test of an autonomous rover in a desert, every breakthrough in solar cell efficiency or artificial intelligence is a brick in this invisible foundation. We are not building the swarm, we are learning how to build. We are mastering the art of living off the land on the Moon, perfecting the closed-loop life support systems that will be essential for any long-term presence, and writing the first lines of code for machines that might one day learn to replicate. Our progress is measured in incremental gains, in patents and papers and prototype missions, each one a quiet answer to a future engineering challenge. The staggering logistics of dismantling a planet begin with a single, shared decision to look outward with purpose. It starts with a culture that values long-term thinking, that teaches its children not just about the past but about possible futures. It requires a society willing to invest in pure research whose benefits may not be seen for 100 years. We stand at a unique point in history, with the knowledge to see the path and the agency to choose whether to take the first step. Our legacy may be that we were the ancestors who saw the star-filled darkness not as a void but as a workshop, and who had the courage to pass the blueprint forward. The staggering logistics we have traced form a single, coherent truth. This is not merely an engineering problem, but a mirror held up to our deepest potential. To unmake a world and rebuild it around a star is to redefine ambition itself, stretching the very fabric of what a civilization can conceive and commit to across time. We have walked the path from selecting a silent, airless world as our quarry, through the silent ballet of self-replicating machines and orbital smelters, to the profound societal and ethical transformations such an endeavor would demand. Each step reveals a tapestry of interconnected challenges, where a solution in robotics creates a new puzzle in governance, and a breakthrough in material science echoes into questions of cosmic philosophy. This project asks us to think not in fiscal years or political terms, but in geological epochs, to plant trees whose shade we know we will never sit under, for the benefit of beings we may not even recognize as our own descendants. It is the ultimate exercise in long-now thinking. While the physical construction of a solar megastructure may lie in the distant, hazy future, perhaps tens of thousands of years from now, the act of planning it has immense value for us today. It expands our horizons. It forces us to solve problems of cooperation, sustainability, and intelligence on a scale that makes our current global challenges seem like training exercises. This thought experiment is a gymnasium for the mind, building the cognitive and cultural muscles we will need for any grand future, whether it involves a Dyson Swarm or not. It teaches us to see our solar system not as a static collection of rocks and gas, but as a dynamic workshop, rich with possibility. The astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. In this vision, that something is not a distant alien artifact, but our own cosmic destiny, a future we choose to build with patience, wisdom, and collective will. It is a reminder that our story does not have to end on this pale blue dot. If this vision of a species reaching for the stars excites you, consider subscribing to join us as we continue to explore the breathtaking frontiers of science, technology, and human possibility.